Okay. Oh, thank you, Raphael, for the introduction, and to the organizers, including Conrad, for inviting me to speak. And thank you to all of you for tuning in. I'm a postdoc at Imperial College in the group of Ian Walmsley. But the work that I'll be presenting today is work that I did during my PhD at the University of Oxford in the groups of Ian Walmsley and Alex Lvovsky. And my work was focused on using photon-number-resolving detectors for quantum state engineering, and in particular for this experiment where we engineered quantum states for quantum-enhanced interferometry. So this work was done in collaboration with the group of Sewu Nam at NIST, as well as Magda Stebinska's group at Warsaw. So today I'll be presenting two experiments mainly. One where we use these photon number resolving detectors to compare Fock states, and I'll then go on and discuss how we use these for quantum enhanced interferometry. And the second experiment was using these detectors to build something called a weak field homodyne detector. So I'll say a little bit about what that is and how that can be used for quantum state engineering as well. But before jumping into those projects, I'll start by talking about our detectors and generally motivating why we want to engineer quantum states. So quantum state engineering for me refers to the ability to control the photon number coefficients of some single mode of the electromagnetic field. And the ability to control these coefficients can let you prepare states that can potentially be useful for things like quantum sensing. So you can engineer states that can be very sensitive to rotations, for example. And also to engineer states which can encode information in a robust manner for things like quantum information processing. And in particular, you want often to engineer states which can be error corrected. And so I'm thinking about things like Gottesman, Kitaev, Preska states. Another nice thing is the ability to initialize your system in some desired state, and this would let you simulate the dynamics of other systems for quantum simulations. So typically the way that we have the ability to control the quantum state of an electromagnetic field is by exploiting nonlinearities that arise through strong light-matter interactions. So in the microwave and radio frequency domains, there's been a lot of work experimentally demonstrating this in a variety of systems, which includes Rydberg atoms inside of microwave resonators, superconducting circuits, and trapped ions. And quite recently, in the group of Rempe in Germany, they showed these strong light-matter interactions in the optical domain and used them to engineer quantum state in the optical domain. So in their system, they trapped a single rubidium atom inside of this cavity here. And owing to the strong interaction between the atom and the cavity field, they were able to engineer the quantum state of light that's injected inside the resonator. So in particular, they prepared their atom to be in a superposition of a ground and excited state. And the result of that was that the state that was reflected from this beam splitter was in this superposition of having received a phase shift and not having received a phase shift. And this is the so-called optical Schrödinger cat state. So the direction that I'm coming from in this problem is not to use such strong light-matter coupling, but rather do quantum state engineering with essentially with simpler experimental setups, so we don't have any single atoms. But the downside is that we have weak nonlinearities. So typically we have to rely on second-order nonlinearities. And because of that, we're restricted in what classes of states, non-classical states, we can prepare. So in particular, we can prepare what are called Gaussian states. So these are states with Gaussian Wigner functions. And if we want to engineer more general non-classical states, then we have to use this process of measurement and post-selection. So to give an example, something which I'm sure most of you are already familiar with, through this second order process of spontaneous parametric down conversion, you can prepare a single photon. So just briefly, SPDC is a Chi2 effect where a pump photon can down convert into signal and idler photons. And typically, if you don't pump the crystal too strongly, then only a single pump photon down converts. And so if you place a detector in one of the down converted modes and that detector clicks, so shows the presence of a photon, then you can herald the existence of a photon in the other mode. So you prepared a single photon. So conventionally, this is done using detectors which don't have photon number resolution, which means that they click whether 1, 2, or more photons are absorbed. And this is fine so long as you don't pump your crystal too hard, because the higher order terms in this state that's produced by the Chi2 interaction are suppressed. But if you had access to number resolving detectors, then you can access the higher order terms in this series. And this would enable multi-photon state engineering. There are other reasons why photon counting is a very powerful tool for the quantum optics toolbox. In general, or broadly speaking, it provides a Gaussian resource. And this is something that's essential for many quantum information processing protocols, including universal quantum computing. It's also a very useful tool for characterizing quantum states. So what you could do is simply measure the number distribution of your light, and that tells you the statistical properties of that light field. So things like whether it has sub-Poissonian statistics and so on. In fact, you can also use photon counting to completely characterize a quantum state of light by measuring the parity operator, which is defined in this way. If you just measure the parity operator, you get the value of the Wigner function of your quantum state at the origin. And so what you can do is displace your state around using displacement operation and kind of raster the Wigner function at different points. And in this way, completely reconstruct the Wigner function. And as I alluded to before, photon counting can be used for engineering multi-photon states, and there's been some work exploring this. So in particular, here in this experiment, a squeezed vacuum state was mixed with vacuum on a beam splitter, and a number of photons were counted in the reflected port. And this has the effect of subtracting photons from the squeezed vacuum. And they showed that you can prepare approximate Schrödinger cat states. And likewise, something which has been gaining a lot of attention lately is this Gaussian boson sampling framework, where this kind of generalizes what I've shown here on the left. You have a whole bunch of squeezed vacuum states and maybe some coherent states, and you send them into a large multi-port interferometer, and you perform some photon number measurements at some of the outputs. And some recent work, including this physical review A from Xanadu, has studied what states you can engineer using this kind of scheme. And they found that you can prepare some really exotic states like these Gottesman-Kitaev-Pascal states, which have applications for quantum computing. So clearly, photon counting is something that's quite desirable, and it's been worked on for some time now. So here's a table listing some of the available technologies. In this table, I've included schemes that multiplex conventional click detectors. And so the idea there is to split your light into a number of modes so that each mode contains no more than one photon. And then simply detecting all of those modes with click detectors. And in this way, you can achieve pseudo number resolution. So at the bottom of the list, we see the transition edge sensor, and it really stands out from all of the other technologies for its really high efficiency. And this is a crucial requirement for photon counting because of this fact that the probability of detecting n photons scales exponentially with the number of photons. So the transition edge sensors are detectors developed by NIST in the group of Savignan. They consist of a thin tungsten film, this blue here, that's embedded inside of an optical cavity designed to maximize absorption, in our case, around 1550 nanometers. So these are superconducting detectors. They operate at less than 100 millikelvin, and so for that we need to use such a beast, this kind of dilution fridge. Unlike other superconducting detectors, they operate in this transition region between the superconducting and normal state of the tungsten. So in this region, the tungsten's resistance is highly dependent on its temperature. And so even if a single quanta is absorbed by the tungsten, this leads to a measurable change in its resistance. And this is what we measure out electronically. So in a typical experiment, we have some pulsed source of light, and we couple that light into an optical fiber and send the fiber to the TS. And we read out the voltage traces produced by our detectors using an analog to digital converter that's triggered by the pulsed light source. And so what we might typically see is something that looks like this. So this is showing the voltage as a function of time triggered by the pulsed light source. And each gray line here is showing a different detection trace. So you can see the detector heating up when light is absorbed and then cooling back down. And you can also see that these traces are showing up in groups, and this is due to the quantized nature of the light that's being absorbed. So when we convert these traces into a scalar value, for instance, by taking the area of the traces, and we make a histogram, we see something like this, where we can see clear bins corresponding to the different numbers of photons that were absorbed by the detector. And so this figure here is actually data for light that's in a thermal state. So TESs are very efficient. They have efficiencies of above 95% thanks to this optical cavity. One of the downsides is that they're a little bit slow, so we can only operate them at about 100 kilohertz. And this has to do with the fact that it takes about 5 microseconds for them to cool back down again. And we can count up to about 15 photons using these detectors. So as I alluded to earlier, one of the things we can use photon counting for is preparing Fock states, so preparing larger photon number states. And the idea is that we're going to place this TS in one of the down-converted modes of this SPDC interaction and try to access the higher order terms in this series. So in order to see those terms in an experiment, we need quite a large lambda parameter, which means high squeezing. And to do that, we use pulsed lasers, which have very high field intensities, and waveguide-based sources to enhance the nonlinearity of the interaction. Okay, so the sources that we use are based on these periodically poled potassium titanyl phosphate waveguides. And these waveguides can be very bright. So we can see up to n equals 8 photons in this series here. They also have a pretty good spectral purity. So the heralded photons can have spectral purities of about 85%. And so one downside of these waveguides is that so far our heralding efficiencies have been limited to about 40 to 50%. So this is heralding efficiency is referring to the likelihood of, say, having a single Fock state here if we counted one photon here. And this is limited mainly by the fact that the waveguide spatial mode has this egg-like shape. And so we're limited mainly by the efficiency of coupling that egg shape into a single mode fiber. So because of that loss in the coupling of fiber, in our experiments, we don't prepare ideal Fock states. We prepare noisy ones, essentially. So what I mean by that is, if we detect J photons here in the herald mode, because of the loss in the heralding mode as well as in the signal mode, we don't have a J photon number state here, but rather a statistical mixture of photon number states. And the purity of that statistical mixture depends on the squeezing, so on this parameter lambda, and as well on the amount of loss. So one thing that we can do in the experiment is actually kind of compensate for loss in the heralding mode. And the idea is to reduce the squeezing of our down converter. So by reducing the squeezing, we reduce the likelihood of getting the outcome J here. But it also means that if we get the outcome J, we've reduced the likelihood that this TS undercounted the number of photons in this mode. Okay, and so that trade-off between the heralding rate and the purity of the state that we herald is shown in this plot here. So the continuous lines here are showing the purity of the state that's heralded for different outcomes J. And the dashed lines, it shows the corresponding heralding rate. And this is assuming 50% loss in the herald arm and 100 kilohertz rep rate. And so this is one of the trade-offs that we can make in our experiments between the purity of our heralded Fock states and the rate at which we can prepare them.
Excuse me, can I interrupt you, Guillaume?
Yes.
So, and concerning this sense transition edge sensors, what is the frequency requirement? So how narrow should be your light? Well, how narrow the bandwidth of the light should be to have them operated properly? And in general, so what is the pulse time? What are the time of the pulses in your case, and what is the frequency distribution in your experiment? Sure.
Yeah. So we tend to work with quite broadband pulses of light. So we pump our sources with femtosecond pulses, and typically our down-converted modes have about 1 picosecond, or about 1 picosecond pulses. TSs have been operated, I guess, both with very short pulses as well as longer ones. So for example, at Xanadu in Toronto, where they detect quite narrowband light using TSs. But in both cases, it's almost always operated in a pulsed regime. So even if you have a narrowband source, you should pulse your say continuous wave laser in order to operate the TS.
Because I'm not an expert, but if I see this plot of this resistance of this superconductor, I can imagine that the frequency is different, and the energy is larger or smaller, and then the single photon with different frequency will cause different readouts, and maybe you can confuse two photons. I don't know.
Oh, I see. So this omega here.
Yeah, sure.
Right. Okay. So I guess the two TSs that are available in the quantum optics community can detect telecom photons, so for 1550 nanometers, as well as 800 nanometer photons. But astronomers use these detectors to measure really high energy photons, X-rays and higher. It all depends on how you design the tungsten and whether or not you decide to put this optical cavity around the tungsten. So it highly depends on how you design these detectors. They're quite versatile in what frequencies they can detect.
Okay, thanks.
Yeah. So we use these photon number states to do an interferometry experiment. So the idea that we had here was to use two different SPDC sources and prepare photon number states, potentially two different photon number states, and inject these into a Mach-Zehnder interferometer, as shown here in the top left. And the goal with such a setup is to engineer a state inside of this interferometer that can be more sensitive to this phase phi here than a classical state. So in other words, surpass the shot noise limit. And we want to do so, of course, in a low photon flux regime. So when we have a few photons interacting with this sample here. And some potential applications for this can be, for instance, characterizing photosensitive samples. So if you have a sample here which doesn't like being exposed to light, then you want to extract as much information about it per photon interacting with it. Okay, so there's been a lot of work on engineering states that can be used for such a task. The issue is that typically these states are quite sensitive to losses. So I'm sure something that most of you are familiar with, Noon states are notoriously sensitive to losses. And so for instance, if this interferometer absorbs, then in fact, the Noon state performance can be worse than that of a coherent state. So you might be in fact better off just using classical light. So what we found is that actually the state that's engineered using this scheme, so by injecting photon number states into the interferometer, can be quite robust to losses. Okay, and this is shown in this plot here in the bottom left, which is showing the quantum Fisher information as a function of the transmission of the interferometer. So here I'm assuming equal transmission in both modes. And for those of you who aren't familiar with this quantity, the quantum Fisher information is a metric which tells you how phase sensitive the state inside of the interferometer is, optimized over all possible measurements. And in our case, our probe can be parameterized by this quantity delta here, which is the difference in the Herald outcomes. And what we found is that depending on how much loss you have in your interferometer, there's an optimal choice for this delta parameter to maximize the quantum Fisher information. And that's what this colored curve is showing. It's showing you the optimal choice of delta for a given amount of loss. And so this is quite a nice feature of this sort of scheme, because it means that depending on how much loss you have in your setup, you can trade away phase sensitivity for robustness to loss by choosing this parameter delta here. And on the same plot, I'm showing the performance of the Noon state, the dashed line, and the optimal state. And the optimal state here maximizes the quantum Fisher information for a particular amount of loss. So we built that experimental setup. We have two different SPDC sources, both using these periodically poled potassium titanate phosphate waveguides. And as I showed before, we send one of the down-converted modes to TES and herald photon number states. Okay, we then inject those photon number states into this device here called the variable beam splitter. Okay, so this is a beam splitter where we can tune the reflectivity and transmission. And the way it works is there's two evanescently coupled fibers inside. And there's a knob here that we can turn to tune the distance between those two fibers. And that changes the coupling between them. And in that way, we can change the reflectance of this beam splitter. And this guy enacts the same transformation as a Mach-Zehnder. So in a Mach-Zehnder, as you change the phase phi, essentially you change the where the light comes out of that second beam splitter, and this essentially does the same thing. By changing the beam splitter, you change the reflectivity. And at the output, we measure we do photon counting. So we send both outputs to TSs. So here are our results. These are results for in a low gain regime. So when we don't pump the sources too hard. I'm showing results for a particular probe here. So this is where we heralded a single photon at both TSs. And so this prepares, so there's a single photon here and here, and this prepares the n equals 2 Noon state or the n equals 2 Holland-Burnett state. And so the different colors here correspond to different detection outcomes, which are shown here, that the circles are data and the lines are fitted model. And so from these different probability or fringes, if you want, we can quantify the sensitivity of these fringes to the phase phi. And we do this by computing something called the classical Fish information. Basically, this uses these curves and tells us how much information we have about this parameter phi using these curves. And in our case, we normalize our Fish information by the number of detected photons. And we do this so that we can easily compare our results to the classical limits, the shot noise limit. And this would correspond to when there's a Fish information of 1 per photon. Okay, so we calculate this Fish information in 2 different ways, which is shown in green and red here. In green, we post-select on cases where S1 plus S2 is equal to H1 plus H2. And so what this means effectively is that we throw away all the cases where we know a photon was lost somewhere. So for instance, if S1 was 0 and S2 was 1, then we know that we lost a photon, say, in an interferometer, and we don't count that event in our calculation of the Fish information. So if we do such a post-selection, we find that our phase sensitivity is above the shot noise limit. However, when we include all of the events, so we don't do any post-selection, then our phase sensitivity is below the shot noise limit, and this is basically due to the losses in our experiment.
Guillaume, can I ask you something?
Yeah, of course.
Because, okay, so I understand that you have these probabilities and you fit the curves and then you compute this classical Fisher information, yes?
That's right, yeah.
So in this way, you don't present the error bars for the classical Fisher in the end.
Here the error bars are very small, so that you can see a kind of shaded region.
Okay. So this includes error bars, yes?
That's right. Yeah. Sorry, I didn't mention that. Yeah.
Okay. Good.
So the next thing we did was increase our pump. And we reached this high gain regime where we can herald larger photon number states. In particular, here I'm showing results for heralding 8 photons. So the top plots here are showing 2 different cases. One where all 8 photons come from one source. So this is the delta equals 8 case. And as well here are results for the case where each source produces 4 photons. Okay, and like before, the different colors here just corresponds to different detection outcomes. And again, like before, we calculate the classical Fish information using these different fringes and others, which I'm not showing. I mean, there's many fringes. So here's the results, and here I'm showing the Fish information curves for different probes, for different delta parameters. And
sorry, Guillaume, yeah. sorry, I'm interrupting you, but when you are fitting, because I mean, you have to have then the form of the curves, yes? What are the 3 parameters you are fitting in the end?
So you mean to fit these lines here in the
Yes, because in principle you have some data, and then you have your model, and I understand that you put some 3 parameters in the model then to fit these curves.
That's correct. Yeah.
classic information.
So our model basically says, okay, we have two mode squeeze vacuum sources, and we have loss in all 4 modes. So each source can have a different brightness. So there's 4 losses and the squeezing parameters of each source. Those are the free parameters.
Okay, okay, thanks. Yeah.
We had a more involved model, which also took into account mode mismatch between the 2 interfering modes. So if you, of course, if you include more parameters, you get nicer fits. When we used that model, we found that the fit parameters agreed with the parameters that we measured experimentally. But it's much slower to do the fitting with that more complex model. So for these curves here, I'm just using the simpler model of just having losses and different squeezing. Yeah, so we found different Fisher information performance for the different probes, and this is what we expected based on the quantum Fisher information curves I showed at the beginning. So given that we have about 50% loss in our experiment, the best performing probe was the one where all 8 photons came from one source. And the worst one was when there were equal number of photons from both sources. And in particular, I think something that's worth pointing out here is that although all these curves are below the shot noise limit, and again, these are calculated without post-selecting, although they're below the shot noise limit, we found that the performance of these much larger n equals 8 probes are actually better than that of the n equals 2 Newton state that I showed in the previous slide. And this really shows that this setup can be used to engineer states which can be quite robust to losses. So looking forward, if we wanted to achieve a quantum enhancement without post-selecting, we would need to improve essentially we need to improve the sources. So we weren't limited by our detectors, which have this very high detection efficiency, but we were limited by the efficiency with which we can couple the down-converted light into fiber. Okay, and this goes back to this issue that the down-converted light has this egg shape. So there's quite a number of potential candidates for sources that could be used to reach this goal. So one thing that you can do is use the same waveguides, PPKTP, but to take a saw and cut a kind of ridge in the waveguide. And this has the effect of further confining the mode of the waveguide to the structure and basically making it rounder. And also reducing the losses of the waveguide. Another option is to use something like a silicon nitride ring resonator. And this is also very nice because it can be integrated onto a chip. And so this sort of platform is being explored by Xanadu in Toronto. And they showed that you can have also very high bright down converters using these ring resonators. Finally, another nice approach is to just use good old bulk crystals and use powerful lasers. And in fact, this is what Jianwei Pan's group did in their recent tour de force experiment, where they showed quantum advantage using photonics. So in that experiment, they actually just used bulk sources and they had quite high squeezing and good efficiencies. So to summarize what I've presented so far, I showed that photon counting and bright PEC sources can be used to prepare these Fock states, large Fock states. And despite the fact that these are inevitably going to be noisy Fock states because of the losses, we showed that one potential application for them is this quantum-enhanced interferometry experiment. And although we weren't able to show quantum enhancement without post-selecting, I think our results do show that the probes are quite robust to losses. And there are some ways to improve the efficiency and as well as the purity of these sources to get to that quantum enhancement. So next, I want to move on to engineering other types of states beyond simply preparing Fock states. And to do this, I'd like to just briefly review what the two conventional measurement techniques are in quantum optics. So on the one hand, we have photon counting, and this is what I've been talking about at length so far. And on the other hand, we often use homodyne detection in our labs. And so this is when we combine our signal with some coherent state, typically from a bright laser on a beam splitter. And then we measure the output ports of that beam splitter with photodiodes. And the difference photocurrent measured by these diodes measures the quadrature distribution of the signal. And so this is typically what's used to do quantum state tomography. So if this is the Wigner function of your signal, this homodyne detector essentially projects that onto a particular axis in phase space, and from these quadrature distributions, which is like the shadow of the Wigner function, if you measure those shadows for a sufficient number of angles, you can reconstruct the Wigner function. So in many ways, homodyne is complementary to photon counting, and that's kind of summed up in this table here. And it would be really nice if we could have a detection strategy which would let us tune from doing photon counting all the way to doing quadrature measurements to explore the region in between these two types of measurements. And there's quite a straightforward way of achieving that, and that's using this detector called weak field homodyne. And so the idea is to replace the photodiodes in the homodyne detector with photon-number-resolving detectors. And so now we combine elements of both strategies. So alpha here provides the phase reference. So now we can perform phase-sensitive measurements. And by changing the strength of this coherent state or local oscillator, we can change what state we project our signal onto. In particular, we can do photon counting, we can do quadrature measurements, and in between those two, we can project light onto a phase-sensitive non-Gaussian states. And this has, as I'll show, some applications for state engineering. So before talking about the state engineering, I just want to focus a bit more on the tunability aspect of the detector. So to investigate that, what we'll do is measure the photon number difference operator, so which is shown here. And so this is the observable that we'll be measuring. And typically, if what's done in homodyne detection is to use a very bright local oscillator. So if this alpha here is very large, then you can apply this approximation called the classical field approximation, where you replace this annihilation operator by its expectation value. And if you make that approximation, then you find that this photon number difference operator becomes the quadrature operator of the signal. And so in this way, you can measure the quadrature distribution of the signal by using a sufficiently large alpha. And so what we're going to be interested in is to find out when this approximation becomes valid and whether we can access that regime using these TSs. So we did this experiment to test that tunability, and here was our setup. Let me start by talking about what's going on the first path here, labeled 1. So here we pumped the waveguides, as I've been showing already, and send one of the modes to a heralding detector to prepare a photon number state in the other mode. So this photon number state will be our signal. And in the second path here, we prepare our local oscillator. And the way that we did this is through difference frequency generation. So we also couple this narrowband continuous wave laser into the waveguide. And through difference frequency generation, we prepare this coherent state. But importantly, this coherent state has the same spectral properties as our photon number state. Okay, and then we combine these two on a beam splitter and then measure the outputs with the TSs. And so here are the results for a particular case where we've heralded 6 photons at our heralding detectors, so our signal is this noisy 6-photon number state. And I'm plotting here the probability to measure a particular number difference for 3 different local oscillator strengths. Okay, and the black here is our data. The red is a quantum model, and this just means that we didn't make any approximations about alpha. So we treat this, we don't make that classical field approximation. The model does take into account the efficiencies of the detectors, as well as mode mismatch between the 2 modes here. And then the blue here is the classical approximation model. So this is when we treat this alpha as a classical field, and essentially these blue curves are the expected quadrature distributions. And so what we find is that, for instance, in this middle panel, we don't see agreement with the data and so we see agreement between the data and the quantum model, but not with the classical model. Okay? This tells us that the approximation is not yet valid. So we're not yet measuring the quadrature distribution. But when we further increase alpha, we find pretty good agreement between all 3. And this shows that we can really tune by changing the local oscillator strength between measuring photon number and measuring the quadrature operator. So we also explored the capabilities of this weak field homodyne detector as a state engineering tool. So the idea is to just replace, instead of just having a photon counter in one of the down-converted modes, let's place the weak field homodyne detector. And conceptually, this looks something like this, where we have a 2-mode squeezed vacuum state, and we send one of the modes to the weak field homodyne detector. And depending on the number of photons measured at each output here and the strength of the local oscillator, we can change the state that we herald in the other mode of the down conversion. So we did this experiment, and in our experiment, we looked at a particular case just as a proof of principle, where we saw 6 photons here, 0 here, and our local oscillator strength was about 15 photons. And here I'm showing the number distribution of the state that's heralded in 2 different cases. So in the red or pink case, we purposefully delayed the coherent state with respect to the squeezed vacuum here. Okay, and this was essentially to stop these 2 states from interfering. And what we saw is that the state that's heralded here when there's no interference looks like a thermal distribution. Okay, and this is kind of what we expected, because it means that the detection outcome 6-0 tells us essentially nothing about the number of photons in this mode, and so we can essentially trace over that mode, and what we are left with is the thermal state here. On the other hand, the blue curve here is when we let alpha interfere with the squeezed vacuum, and we see a drastic difference in the number distribution. And so this really shows that the state that's heralded not only depends on the detection outcome here, but it also depends on the interference between the coherent state and the squeezed vacuum state. So we didn't push this experiment much further, and part of the reason was that we didn't have a means of fully characterizing this state psi h beyond just measuring its number distribution. But we explored it a little bit more in depth in theory. And what we found is that we can engineer states here, psi h, that have even parity, so that are only made up of even photon number terms. And this happens when we choose the detection outcomes at the output of the beam splitter to be equal. And so, one way to understand why this occurs is to think about the scheme in reverse. So if you imagine 2 n photon number states impinging on a beam splitter, there's this really interesting interference effect that happens where the output modes of that beam splitter only ever contain even numbers of photons. And this was first, as far as I know, this was first mentioned in this PRA here. So, and this is also sometimes called the Holland-Burnett state. And because of this pairing interference effect, it means that the state that's heralded here will only contain even photon number terms. And it turns out that when you inject a coherent state in the input port of the beam splitter, what you're doing is projecting this mode here onto a coherent superposition of alpha and plus minus alpha. So by picking out only the even terms in alpha here, you symmetrize it, and so you project onto a symmetric version of it, which is this Schrödinger cat state. And so using this, you can not only project light onto Schrödinger cats, but you could also prepare Schrödinger cats in the herald mode. And so this is a theory plot showing the fidelity of that heralded cat as a function of the size of the cat. The blue circles here are analytic results, and the black is a numerical result where we optimize the, we look for the best parameters n and alpha to maximize the fidelity. Okay, and on the same plot, we're showing the probability of obtaining this herald outcome using the best possible squeezing. So we maximize this probability of heralding the cat. And so we were quite pleased to see that this scheme has this nice feature that the fidelity of the cats actually gets better with increasing cat size. And this has to do with this interference effect, essentially.
Yeah, we should be finishing
soon.
Soon.
Okay. Nearly done. Sorry about that. So just very briefly, we looked at further extending this scheme. So what we did, what you can do is concatenate multiple instances of the scheme. So for instance, we can prepare a Schrödinger cat using what I've just shown you. And then, so that cat would be here, where it's labeled 2. You can then displace that cat in phase space and use that displaced cat state as the input for another instance of this state engineering scheme. And because of this symmetrization effect, you can prepare these more complex 4-component cats, which is just a symmetrized version of this Wigner function. And these 4-headed cats are quite interesting for quantum information processing, because you can use them to encode a qubit in an error-correctable manner. We also, of course, everything I've been discussing so far is neglecting the effects of loss, but we looked at what happens when you include the effects of loss, and essentially, it's what you expect. I mean, cats are notoriously sensitive to losses. So this is showing the fidelity is a function of the efficiency of the detectors and the size of the cat. And on the bright side, though, I should say that photon counting with TS is quite remarkable in that we can count lots of photons with a very high efficiency. So I still think that this is a worthwhile way of preparing these interesting cat states. Okay, so with that, I'd like to summarize. I talked about how these photon number resolving detectors can be used to prepare this, to build this weak field homodyne detector, and showed that this detector is quite versatile and can perform both photon counting and quadrature measurements. And the region in between those two measurement regimes, you can project light onto phase-sensitive non-Gaussian states, such as Schrödinger cat states. And just before ending, I'd like to acknowledge my colleagues who helped me on all these projects. In particular, Monica Mycroft was joint first author with me on the quantum-enhanced interferometry project, and also David Phillips, who helped me operate the dilution fridge to cool the TSs. And with that, I'd like to thank you for your attention, and I'd be happy to answer any questions.
Okay, so thanks a lot for this nice talk. We have some time for questions, so please. Okay, you can just unmute yourself or write on chat or whatever you want. So any question? Because I have a lot of questions, but I already asked a lot, so so I don't want to ask more. Okay, so maybe, yeah, so maybe I will ask anyway. So, okay, when working in quantum interferometry, we know that in the limit of strong light beams, the optimal scheme is to get optimal quantum enhancement in presence of losses, is to mix, take coherent state and squeezed vacuum state. And this is what is done in LIGO and everywhere else in practical like applications. So now, of course, this is in the limit of strong beams. When you are focusing on this 8 photon or 10 photon or something like this, I was wondering if you thought of comparing your setup with this, because your setup basically tries to fix the photon numbers, to have some definite photon numbers at the inputs, okay, and then see what happens. But I'm not 100% sure that this is not too restrictive. Like, okay, why do we really want these fixed photon numbers in the first place? Yeah, so for example, especially comparing with your second part of your talk, why not try to use your, I don't know, non-linearities to just produce squeezed vacuum, weak squeezed vacuum and weak coherent state, mix them, and then use your transition edge sensors to have photon number detections and compare the performance of this without the explicit requirement of this fixed photon numbers in the beginning. And we know that for strong beams, it will be optimal scheme.
Yeah.
Now for this intermediate, it will not be optimal probably, but maybe because you don't require this restrictive conditions in the beginning, maybe it will be more practical or better.
Yeah. Yeah, I agree with you in that, and like there's no reason to restrict ourselves to states that have definite photon number. And in fact, what you can do, and there's a recent experiment from Thomas Garrett's who looked at this, is to just have a single source, so like here, and use the 2-mode squeeze vacuum state that comes out of that, and inject that into an interferometer. Okay. And in fact, that state is even more robust to losses than the definite photon number state. So in general, indefinite photon number states are better than those with definite photon numbers. The downside from an experimentalist's point of view, I guess, is that you don't have access, you can't really control, let's say, the minimum number of photons that you inject into your interferometer. So what I mean by that is if you have an application where you really care about having the maximum Fisher information per photon, then in principle, you'd want to inject a fairly large state into the interferometer all the time. But if you use these squeezed vacuum states, then the most likely terms are lower photon numbers. And so in most outcomes, you'll get smaller photon numbers.
Okay. Thanks. So any other questions? Okay, I don't see any. Okay, so once again, thanks a lot for this talk, and hope we will meet some point.
Yeah, likewise.